All right, well, today is our review session. Hunter is diligently working on your submissions from last night to get those turned around to you today, so that you can see feedback. So that you can target study any aspects of trees that you realize that you don't understand as well as you thought after getting back that feedback. And if you have any questions about that feedback or about what could have been done in its place, since we're not meeting between today and the exam tomorrow morning, shoot me an email. I might have availability to meet with you remotely if that's not done by the time I have my 1 to 2 o'clock office hours, or you have to run off to something else. But I guess we can start with who has questions.
How many points are on the exam?
I actually just figured that out a few minutes before walking in here. I had made it yesterday, but I hadn't assigned points to anything or spaced it or been ready to print it, but I settled on 108.
Go through the advanced sorts again,
Yeah,
kind of like how it works.
yeah,
Because I want to make sure I understand.
yeah, that's a very good idea.
I'm trying to think about it in my head, like.
Yeah, so advanced sorts, Connor, I see your question in chat as well. I will put that in the queue of things to talk about. The question has to do with the fields and methods of the queue, so I will put that question itself in a queue, and then we'll have what, a recursive queue. There's a joke there somewhere. So the two advanced sorts we covered are merge and quick sort, and to make sure that I'm doing this on, how much space do I have on each side of this? Right there. Okay. So we'll do merge sort over here. Then we'll do quick sort over here. All right, who wants to walk me through how merge sort works? Yeah.
So say you have an array list, or an array list of size 8. Then you'll basically just keep splitting it in half every single time until you get down to just single node, and then you'll recursively work your way back up, and it'll have a, forgot the exact word, but there'll basically be 3 pointers or 2 pointers.
Yeah, we need to reconstruct the position of the array.
So then we'll have one on the left half that we split, and one on the right half, and then we'll just compare.
So in general, we're going to be, if we talked about something like the steps that we needed, we would need to find the midpoint. We're going to recurse on left half. We're going to recurse on the right half. Then we're going to merge sorted left and right halves. So that's basically the English description of merge sort. We're finding the midpoint, recursing on the left half, recursing on the right half, and then merging into a sorted array. And as we know, in recursive algorithms, if we're actually going through an example of this, we don't go through these steps. We wait until we have a recurse on step, and then we put it on pause, and we restart with that smaller subproblem, keeping track of where we were in the larger subproblem. So step 1, find the midpoint. We want to split the array kind of right here, so that we have a left half and a right half. We are then going to recurse on the left half, and since this is a recursive step, we're kind of going to put step 1, the size 8, I'm just going to kind of draw an 8 here, as the size 8 array is paused at this waiting to return from the recurse on the left half part. So we're going to recurse on the left half. Coming in, we have an array of size 4. So we're going to find the midpoint of that array, splitting it into a left and a right. Now that we've studied trees, this is going to start to look like a tree, which gives us a left half and a right half. And we're going to recurse on the left half. So we're going to be stuck at this position in our size 4 array. And we're going to now worry about this subproblem. We're going to now take a look at this and say, okay, we can split this into a left and a right half. Here's the midpoint, so here's the left half and the right half. So we're going to pause our size 2 at the recurse on the left half. We already know that this is sorted because we have an array of size 1. So there's an if statement in there that says if the size of the array that is passed in is less than or equal to 1, then we just return. We know that it's already sorted. So we come back to where we were in the size 2 array, which was on this line. We've now returned from the recurse on the left half. So we're going to move forward. We see another recurse. We're going to recurse on the right half, right here, which is going to put a pause on our program as we restart from here. And of course, this is of size 1, so we're able to just return from that. As we return from that, we're going to move on to merge the sorted left and right halves into the original array in sorted order. So we are going to take this value and this value, and we are going to now put a pointer here, and pointer here. And the goal is to ask, is this less than this? If so, this goes here. Is this less than this? If so, this goes here. One of those two has to be true, since this is an array of size 2. So we are going to end up with a fully sorted array. Once we're done with this, this is either going to be out of bounds, in which case we take the rest of this and fill it to the rest of this, or this is now going to be out of bounds, in which case we take this and put that here. Regardless, at the end of either one of those branches, we end up with an array of size 2 that is sorted. And we say yay. So we're able to kind of erase this because this is no longer relevant work. We know that this is now sorted. So we return to the call that came before it, which was the size 4 array. And now we have finished the recurse on the left half. We know the left half is sorted. So we can move forward with our size 4 problem and recurse on the right half, which is going to restart a brand new problem of size 2. So we are going to find the midpoint, split this into a left and a right half. Recurse on the left half. So now we have a new 2 that is stuck here at this point in the code. So we now can look at the left half and the right half of that, since they're both of size 1. The size 1 problem is going to get stuck here for very long. We're going to determine that these are already sorted, come back. So we recurse on the left half, we recurse on the right half, and now we're down at the merge sorted left and right. So we're going to merge this into that via that same logic that we talked about. Granting this has done, this has done. And now we return from recursing on the right half from the problem with size 4. We then go through the merge process of the size 4. So we come back to this line, continue the size 4, moving down here. So now we put pointers here, and here, and here, and we're going to be figuring out if this is smaller than this, then write this here. If this is smaller than this, write this here. We're going to continue that process all the way through until this array is filled with these 4 elements in ascending order. Once that's the case, we can kind of get rid of this work. We don't need any of this anymore because this array of size 4 is now sorted. As we do this, we return from the recursive call to the size 8. We finished the recurse on the left half part of this 8. So we're ready to move on. So the 8 recurses on the right half, which now we have the right half. So we're going to kind of draw this out as this subproblem, and we're gonna go do exactly what we just did, this exact same problem of size 4. We're gonna restart our size 4 problem of finding the midpoint, recursing on the left half, recursing on the right half. Once that's done, etc. So the exact work that we just did, we're gonna do that again, and that will get that array of size 4 sorted. Once we do this, this will have fallen all the way through this logic. We return to the 8 at the line that we stopped, finishing the recursing on the right half, and we move down now to merging this array into that array. And that will give us the fully complete.
Are you gonna have something like last test with the source where we walk through the steps? Are you gonna have something like that with?
Maybe. I would say that that is something that I could ask you.
What was the time complexity for merge?
This is, let's ask the class, what is the complexity of merge sort, and how do you know? It is n log n. How do we know that it's n log n? What's the intuition behind why it's n log n?
Because you get split in half every.
Yeah, so there's this concept in computer science called divide and conquer. There's a whole class of algorithms called divide and conquer. In fact, it's going to be an entire section of your algorithms, your 320 class. It's going to go over different divide and conquer algorithms and how they work. But the idea is that we take the problem, we divide the problem into subproblems and then conquer those subproblems. Once we have divided the work and finished the division, we conquer the result. So divide and conquer is how that works. So yeah, if we were to imagine drawing this out as a tree, let's actually draw the full scope of the tree so that hopefully we can tie this to what we talked about in trees. How many total cells are there in this tree? So there's 8 here. If we are to add up all of the total numbers in the tree. 32, so there's 32 total numbers here. This is gonna be proportional to, we said that n equals 8. My off the screen here now, I might be off the screen, looks like I am. Rather than try to fix what I've done, there we go. So for a problem of size n equals 8, what is the log 2 of log base 2 of 32? 2 to the power of what equals 32?
5.
We have 2, 4, 8, 16, 32. So how did this scale? It's the power minus 1, basically. The power minus 1 is a constant. If you take 2 to the n, how is that different from 2 to the n minus 1? That's a constant. As long as this stays n minus 1 forever, this is a constant and can be ignored. So basically, for this multiplier from n equals 8 to get to the total number of cells in the structure is based on, it scales based on the log of the size of n. So you take 8 times the log of 32, but that power minus 1, and you get the total number of cells that you need to consider in merge sort. If you were to compare this to an algorithm like selection sort, how many cells do we need to consider for selection sort?
Just the length of the array.
So it was the length of the array to find the minimum element. But then you need to find the second minimum element, and the third minimum element, and the fourth minimum element, and the fifth minimum element. So we had 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2. What is that? That would be 3 times, that would be factorial, that would be awful, we would never want to sort that way. So we have 15, 21, 26, 30, 35. It doesn't look like it's that different. And that's why it doesn't really matter what you do if the array is small. But now let's say that the array is 1024 elements. How many cells would be in this total tree if we had 1024 in this first row? So 1024 is 2 to the 10. So we would split this up into half, all the way down to size 1. So there would be how many rows? We split 1024 down to 512 on row 2, 256 on row 3, 128, 64, 32, 16, 8, 4, 2, 1. We ended up with 11 rows. So we have 11 rows times 1024 elements. So that's a little more than 10,000. But now, what is the sum of 1 plus 2 plus 3 plus up to 1024? That's equivalent to 1024 times 1025 over 2. What is that? About 500,000. If we just take that as 1,000, that is 1,000, it's a million, million over 2 is about 500,000, so a little more than 500,000. So we go from about 10,000 to about 500,000. So merge sort is 50 times faster than selection sort with an array of just 1,000. So that's how the logarithmic scale here is so much better than n. It's not really apparent at a size that I can draw on the board, but as soon as you go into implementing it, the math just starts, it becomes very apparent and very obvious that merge sort scales significantly better. Questions on merge sort or the logic or intuition of why it scales better? All right, let's talk quicksort. So in quicksort, is all of that visible over there? Not really, it's a little bit, the light's shining right on it. Can people see that remotely? Did that all make sense? Feel free to ask questions if anything can be explained better or visualized better. So for quicksort, we still have an array. We'll call that 8 elements. It's a very big last element. How did quicksort work? So where is a valid pivot point? Does it matter where the pivot point is? If so, where should we pick it?
Usually at the beginning of the event.
Yeah, that is exactly right. So the actual place of the pivot, we only pick the first or the last because it's the easiest one to just go grab in constant time. We don't have to iterate, we don't have to make any assumptions about the length of the array. The first and last, we have an easy constant way to access regardless of the length of the array, but it does not matter where that pivot comes from. You could choose the second element. You just have to add an if statement that says, if the array's length is at least 2, grab the second element, else you need another place for the pivot to come from. We don't really like that, so the first and last elements are the best places to pick the pivot. Let's say we're picking it at the last position. So here is going to be the pivot. What do we do to put that pivot in place? The goal of quicksort this first iteration of quicksort is to swap the pivot into the place that it goes, and then we no longer need to consider the pivot. We know that it's in the correct place in the sorted array.
Get everything that's less and greater.
Yeah, we need to figure out, all right, what's less than the pivot, what's greater than the pivot. So the way that I like to intuitively do this on paper is to put a pointer here and a pointer here. And the idea is that we're going to move these toward each other until they converge. So this pointer is going to be moving in this direction, this pointer is going to be moving in this direction, and we are searching for an element that is greater than the pivot here, and an element that is less than the pivot here. Once we identify that position, we stop that process. So this is going to be moving up, 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 until it identifies something that is greater than the pivot. Let's say we find it in the very first position. Same thing here. We're going to continue, let's say that we find something that's greater than the pivot in the first position. We move this pointer one space to the left and we find another element, we find something finally that is less than the pivot.
Can we actually put some numbers in there?
Sure. Shout some stuff out.
So. -2.
And the pivot value probably somewhere in the middle-ish.
Zero.
8. 8 will work slightly better for our. 0 would work, we just be the second less element. Note that regardless of how quicksort works, it doesn't matter what the pivot is. It just works illustratively best to understand we're gonna have the most swaps and the most to do if we pick something that's fairly close to them. So, all right, now we're gonna be searching for an element that is less than the pivot on the right and greater than the pivot on the left. Luckily, we luck into it right away. So where this low pointer is pointed is at something greater than the pivot. 12 is greater than 8, -2 is less than 8. So if we want everything that is less than the pivot to be on the left, and we want everything that is greater than the pivot to be on the right, then we know that these two elements need to swap. So we're gonna swap the -2 and the 12. Now we can bump this up and bump this down and consider again. And hey, look, we did it again. Except that now we have both of them being where they belong. 7 is less than 8 and 15 is greater than 8. So you would probably do this with one and then the other. Let's start with the low. We're going to move right until we find something that is greater than the pivot. So this would be less than, greater than. We're gonna stop. And we're gonna move this now left until we find something that is less than the pivot. So we're going to go here, here, and stop. But note now that our high and our low have swapped positions. They crossed over each other. So this means that where low currently is where the pivot gets swapped into. Because we know that what low stopped at is greater than the pivot. If we're going to swap it with the pivot, this is to the right of the pivot. So what goes here needs to be greater than the pivot. What is guaranteed to be greater than the pivot when they cross over? Whatever we point at with low. High stopped at something less than the pivot. Note this would be exactly the opposite if we pick the pivot to be the first value. We would want to swap with something lower than the pivot. What's guaranteed to be lower than the pivot? The value of high. So this is not always the case. It does depend on whether you pick the first or last element of the pivot. Since we picked the last element that goes here, something greater than the pivot, low contains something greater than the pivot, will always contain something greater than the pivot. So we're going to swap the 8 and the 9. The idea is the 8 is now right where it goes in the final sorted array. We know that. We don't know about the order of these elements over here, and we don't know about the order of these elements over here, but we can finalize this slot 8 as saying this is part of the final sorted array. It's just done. You don't need to consider it anymore. So now we are free to recurse on the left half without the pivot, because we don't need to consider the element of the pivot anymore. And the right half without the pivot, because we don't need to consider the pivot anymore. So what becomes the next level of this is this array of size 4 and this array of size 3. Now we are going to recurse again and choose new values of pivot here and pivot here. And then we're going to do exactly the same logic to this. Once we have the pivot in place, we know that that is the place within this subarray as well. So usually this is done rather than copying the array or making a new array, you just pass in indices in the original array. And that way, when the pivot becomes in place, it's already in place in the original structure. There's nothing that we need to do to it to move it back to the original structure. So arrays are usually passed by reference anyway. So if you pass the array and the associated indices that we are considering, these aren't actually separate structures. We're just basically doing the equivalent of a shallow copy. It isn't even really a shallow copy. We're just passing in indices of this original structure. So if we identify this pivot actually goes here, then we know that this spot is finalized because this is actually part of this array. Does that make sense? Does anyone want to see this go further with quicksort, or do we feel like we understand how quicksort works in general?
I feel like I understand.
So I was gonna just do one for my paper while I was listening to you. So what if you get into a situation where it's like your last 3 elements, if you start with the pivot at the end,
Yeah,
is like 2, 3, and then 1. How would that sort of work?
yeah. So we're gonna start, we know we're not considering the pivot. We're gonna start our low pointer here. We're gonna start our high pointer here.
Why is that different from the one that's above?
So we're just not considering the pivot. We started high here, we started low here. And then eventually they crossed over.
Oh, okay.
So we eventually want this one to be swapped into this position. So we're going to look for a position here is greater than the pivot. Yes, so we want low to stop. Is this less than the pivot? No, so high is now going to move here. They swapped over. High may end up going here, depending on your implementation, but it doesn't matter. Now we swap the pivot with the low. And the pivot is in place with respect to that array of size 3. We would then just have a single recursion. We wouldn't recurse on a left half because the left half doesn't exist, it's of size 0. We would have a single recurse of size 2. Does that make sense? It's all about when that low and high swap over or swap positions. Now, this is not how most people actually do this in practice, and I don't know why that is. To me, this is the most intuitive version of quicksort. How many what, sorry? Coding questions? I would say less than or equal to 2. I would say that 2 is probably the most I could reasonably throw in an exam and expect you to be able to complete within 50 minutes. So between 0 and 2. Are we still on quicksort or are we moving to something else? I want to tackle the question remotely about the fields and methods a queue has, and then I will come back to that question. So looking at a queue, What are the fields and methods?
NQ, DQ, peak, size, is empty, and then you can have it contains.
Yeah. So basically exactly that. So we had an NQ, we had a DQ, we had a peak, a size that is empty, and possibly a contains, but there's no way that a contains could run in the order that we care about.
What's the complexity for each of the Q functions?
That's a good question. What do we demand of a queue? Any queue implementation. It's not a queue unless each of those operations run in what time? Constant time. Yeah. So that's why if we have something like an underlying, so I guess the part that's missing is what's the field?
Would you say constant or?
Constant time. Yeah, each one of those needs to run in constant time. Otherwise, you have a list, not a queue.
You go for fields too.
What is the field? Yeah, there's only a single one, really. I guess there's technically a size.
The size and the underlying list. And
Yeah.
Give an array list, the two other ones.
Yeah. So if there's an array list, then there's some additional information that we need to care about, but either it's some kind of list.
How would we draw a queue? Is it just like a stack with?
I tend to draw queues kind of either, if it's a very basic visual queue, I tend to do something like this. Where it's obvious now where the NQs are and where the DQs are. But if you're going to use something like a circular queue, then yeah, I draw it like a circle. With a circle inside of it, and then you can have something like this, depending on the size that, this is obviously way too many elements. But you can see now that you would have a pointer for the place to add to the list. Like this is where the queue begins, and here is where the queue ends. This would say that this element is the front of the queue, this element is the rear of the queue. So we would have a front. We'd have a rear. If we wanted to NQ from here, where would we do it? Past the rear, then I guess we're pointing the rear at the next place to insert, or is it the last element that has been inserted? So usually the way that I would implement it is, this is an element in the queue, this is an element in the queue. So you want to add one, mod the list size to figure out where this is. Then you're going to make the rear point there, and that's an NQ. If you want a DQ, where would it go? Or what would happen?
You remove the front.
We move the front up. Note that we don't actually have to change any of the underlying values. You can have values that stay in here. Let's say we had the number 13 randomly in this. It can stay there. If we were to print out the elements of this queue, we would start at the front and go to the rear. 13 is not in that. In order to loop all the way back around for the rear to do something in here, we'd be putting something in there. We wouldn't just move the rear pointer without writing to that cell. So we don't need to worry about changing it to null or removing it or changing it to some, what is the value of something that's not in the queue? Doesn't matter.
Does the queue always have a capacity field or?
It should, if you're in an array list, because if you try to add to it, you either need to NQ when it's full, you need to throw an exception, or you need to resize the queue.
So less important if it was a linked list.
Yeah. Yeah. Because you don't need to resize a linked list based queue, maybe.
Yeah, that's what I could.
So I guess it is maybe gonna be able to camp. Well, does the front and the rear share the same spot at the beginning, right? Or does it not matter?
They do share the same spot at the beginning, yeah, there's nothing in it. So you could either say that they're pointing there with nothing in it, or they're pointing at the next position for it, in which case. That's a
The rear
little
will
stuff,
not be-
the rear is, yeah,
And
you could set them to be null initially. And then once the first thing is added, then set them to point at that position. Yeah, that's the concept of this circular queue. You note though, that this is really a structure that looks like this. We have an underlying list, so it doesn't actually internally look like a circle. You can't just always move to the next element in a circle, and so we need to consider that if we reach the last element in a list, we need to mod it by the sides to get back to the front. So anytime you are adding to a position in a circular queue, mod it by the size. Not the size of the queue, the size of the underlying structure.
What would be the difference between good or bad hash functions?
So the example that we used had something to do with like phone numbers. We talked about using the first 3 digits of a phone number as a really bad example of a hash. Because all area codes would hash to the same location and we would get a massive cluster. Lots of collisions as we try to insert all of those phone numbers. It's a pretty even distribution though of the last 3 digits. So if you're designing a hash for something, just in the back of your mind, think about that design of what is a good hash function and what is a bad hash function. Maybe come up with an example of some outside of a phone number. What else could you reasonably want to hash? Maybe something like a ticket number. And ticket numbers are gonna have digits that all start with the same few digits for a while. And the ending digits are gonna be what changes. Think of some additional examples of some things like that. How else could you apply good hash and bad hash?
Security number.
Yeah, everybody share theirs.
For
Yeah.
height, does it start at 0 or 1? Because the slides say the amount of edge connections determines the height number. So if you're at the root, it would be.
Height 0, yeah, yeah.
Just double check.
What are the applications of hash tables?
So the ones that we talked about are sets and maps use sets for the keys. But really, anytime that you're trying to store databases, everything that's in a database is basically either a set or something that you need to store lots of information in that database. So you will see hashing come up a lot in 327.
So would SQL be, would SQL be a hash table?
By itself, no, but the underlying data that is being stored, SQL is a language for accessing that. But the actual structure that's doing that, I guess some aspects of SQL interact with hashing to grab you the chunk that you want, but that's not as, yeah, it happens.
So it's more of just the actual database rather than the language.
Well, the database is a table, and then accessing what you care about in the table, or whenever you store something new in the table. Or delete something from the table. SQL is mostly about read access. You wanna be able to figure out and return a slice of a table. Only return the data that you care about whenever you're modifying the table, inserting new elements or deleting elements from that database. That's when you care about hashing, because we need to know where it's stored in the database.
Can you go over like a quick tree traversal?
Yeah. What kind of traversal do we find to be the least intuitive? We have everything we need from the board,
Post order.
post order?
I think.
Yeah. Sorry.
So my preferred one for this, my preferred type of tree involves something that is perfectly in order, it only contains what it needs. So the way to fill it out is in depth first search order. So if you've ever wondered how I fill out the tree when I do all of that, it's in exactly depth first search order. So we do like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It's in order, but also depth first order. So it's something else to tie what we talked about in together. So if we want to do a post order traversal of this, then we want to visit the left first, then the right, and then the node. So we're doing a regular left to right read order, and then where the n is tells us that this is the post order. A pre-order, the n would come before LR. There are additional traversals that go from right to left, but we haven't really discussed them or care about them too much because they're the exact opposite order of the left to right version of swapping the L and the R. Everything we talked about, the L comes before the R. It's just a matter of where the N shows up. Pre-order is first, post-order, and then in order it's in the middle. So we want to go left first, then right, then visit the node. So what is the first node that is output? 1. We go left here, left here, left here. And then there's no left, there's no right, we output the node. One other way to visualize traversals is I kind of at each node level start to write this, and that tells us what the next thing to do is. So now that LRN is here, we're free to return. So the next thing to do after L is to go R. And here, there's no L, there's no R, so the next thing to do is to output the node. Coming back, we've already done the L and the R, so the next thing to do is the N. Yeah, then we come back here, the next thing we do is go R. So we go right, the first thing we do is go left. Since there is a left, there's no left, there's no right, but there is a node. We're gonna output the node. Since we're done here, we come back. Next thing to do is the R. There's no L, there's no R, but there is an N. Coming back, we've done the L and the R, so we do the N. We've done the L, now we need to do the R. L, 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 R, N. R, L, R, N. Whenever we have an N, we're writing. Come back, do the N. Come back, do the R, do the L, R, N. R, L, R, N. Come back, do the N. Come back, do the N. Come back, do the N. That's sloping horribly. But that's how I think about
Do you think you go over a level order?
it. Yeah,
The
you?
yeah.
Could we delete 14 from this?
Yeah. Yeah, we can delete 14. So I guess that's probably the easiest kind of two-child delete. If we delete 14, we basically have two options. We either bring up the left child or the right child. So here, if we brought up the 13, we delete the 14, replace this with a 13, and get rid of this node. Already done. The harder part is if we have two children that have additional children. So if we wanted to delete the root from here, for instance, then we're gonna end up orphaning something and needing to reinsert that orphan. So if we delete the 8, I don't know, we're bringing up the left child or the right child? You get to choose.
Do
Yeah. Well, we're bringing up the right, we're getting rid of the 8 regardless. But the idea is, as this 12 comes up. As this 12 comes up. This entire subtree no longer goes on 12's right child. So there's no way to do this. We can take the entirety of this structure minus this and just bring it up. So basically we say this 12 goes here now. And this 12, this node is gone. We just add this connection right here. But where does the 10 go? If we were to reinsert the 10, where would it go?
13.
So 10 is less than 12, greater than 4, greater than 6, greater than 7. So actually, this connection goes right here. So we're just gonna move this subtree right there. Since everything that's with 10 is still in its correct order, and we know that this greatest value is still less than this because it was on its original left subtree. So everything in this subtree has to be less than 12. So we actually go, this 7 is left, right, as far as we can go until we get to a null child. That's how we know where this is going to go. We don't have to necessarily reinsert it. We just, starting at the node that we originally deleted, we go left, right, until we can't. That's where this subtree goes. And so we're just going to put that in with a 10, 9, and 11. Note that all you have to do is insert the 10. Since 10's connections, its left child and right child already exist, you don't need to worry about reinserting each one of these nodes. This entire substructure is already connected. So you just basically say that 10's parent, instead of being the 12 that it used to be, 10's parent is now 7. And 7's right child is now 10. 10's children didn't change. 9's parent didn't change. 11's parent didn't change. Nothing about the pointers in our structure actually changed, except that we needed a new child that is 10, and 10's parent changed as well if we're storing the parent. So that's the 2-child delete case in its most difficult form. Now this entire substructure is gone. And this is horribly imbalanced, but we'll talk about that now. Questions on the 2-child delete? Before we do a quick level order? Erasing my whole tree, I'm gonna have to make a new one. But we can make a smaller one for level. Since we're not doing anything insane. Let's say this is our tree. 1, 2, 3, 4, 5. So we're gonna keep track of a queue. The queue is gonna tell us everything that we need to do. So level order, the first thing you want to output is the root. So the very first thing that you do if you're writing this in code is you're going to put the root in the queue. When you take something out of the queue, so now we're going to start the loop. The loop is whatever is on the front of the queue. Take that out, output it, and put its left child and right child into the queue in that order. Looping around. Take what is in the front out of the queue, output it. Take its left child and right child, put them in the queue. Looping around. Take out the front thing in the queue, output it. Put its left and right child into the queue. If the left child or right child are null, do nothing. Looping around. Take out the front thing in the queue, output it. Put its left and right child into the queue. They're both null, so we do nothing. Looping around, take out the front of the queue, output it, For its left and right child, put those into the queue. Moving around, the queue size is 0, we're done. So there's your level order traverse. All right, that's the time we have for class. I will throw this recording up on YouTube. I have office hours starting now. If you have any other individual questions or other things that you'd like me to go over, I will gladly do that for the next hour. Tomorrow for fun.
So for quick sort, we do recur, we split it at the end or?
Yeah, you're gonna recur from the left part and the right part.
Yeah,
They're not
I go.
necessarily halves, but on average, they're going to be proportional to the size of the list. So that's what gives us that same n log n behavior.
And on worst case, it's n squared, right?
Yeah, if it's already completely sorted or in reverse sorted order, then you end up with an n squared. Yeah. It's just very unlikely you're going to see that in practice if it's remotely randomized.
May you say worst case was in reverse order and what?
Or in order. Because then the pivot's gonna be swapped with either the first position or the last position every single time.
Oh,
Where should was.
Merge sort doesn't really have, since it's splitting things up, it's always.
So it's always.
Yeah, worst case is that one.
quick sort is preferred for arrays. It's the preferred one.
Quick sort's preferred in general for efficiency. Quick sort is on average faster than first. There are fewer comparisons and swaps as long as it's relatively random. Which is why C++ uses it. Basically, if you ever want to know what is the more efficient of, just look at what C++ does. What's more efficient? Every design decision in that language is about efficiency.
It goes the higher, is that the one that's at the back, if there is one below?
Yeah, H starts out at the very right. The thing that's left of the pivot, if the pivot is the last thing, we don't need to consider the pivot.
Oh.
Yeah. I would say, please, if you'd like to do so, send me an email about the level work, and I can probably relate the fix. So we'll see what I generally let people resubmit once, so maybe I say, I'll let you choose one, and then there's gonna be a last assignment. And if you submit that, you submit that.
Is that one?
Yeah, the last one. Yeah.
I didn't get any comments.
Yeah. If I could keep the lessons, I mean, he said, I can do that. Yeah, that's your. Asking the comment.
You get one, you got it. Yeah. I got to give you the first one. Mine is collisions are handled and not starting with 0, but from